So far we have seen some circuits like this as examples, and we have sort of mapped the kind of circuits that may arise from configurations like this, which you will encounter in your recordings. You have, or we have rather, seen how we can use simple setups to test the circuits in the lab, right? Now sometimes it may be so happen that you don't have access to all these kind of elements, though later I will tell you that these things are not very expensive. People who are very keen can procure them and using them in the lab in your home. Now suppose you don't have access to these kind of materials. You can still, and you're still curious to see, okay, how will such a circuit function, right? Without actually setting it up and without actually writing down the equations to see the behavior. So the quick way to do that, if you have a mapping from the physical configuration to a circuit elements like this, would be to use something called the circuit simulator. Okay, here is circuit simulator which is easily available and freely available on the net, called LT Spice. So LT Spice is downloadable. If you search for it on the website, you can find it. And here is a screenshot of how you run simulations in LT Spice. I will show how to go about doing this briefly. And there are a number of tutorials available on the internet for you to follow. Now, suppose the circuit is not easily mappable from here into such circuit elements, then you may actually use a more physically realistic situation where, for example, if you have a neuron, for example, you are encountering a situation where, okay, you have a neuron, you have cell body here, and you have an electrode fitted into this, and so you have a high impedance here, and there is a high impedance here, right? And then of course there's a large capacitance here, and of course there may be channel conductances here and so on, right? Now if you are bothered by such circuit, right, where you need to actually incorporate more realistic physical configurations, then you may want to use a neuron simulator. And in theory, we have seen how a neuron simulator functions. Like, so this is a basic element in a cable in neuron, and it is sort of capturing this kind of a circuit, and you can have more number of segments to have more detailed resolution of how potentials and currents change over this length, right? And we have seen the theory regarding this. So we may be using such a circuit to test how the system will behave, right? So here is a single neuron with soma and a dendrite, and under voltage clamp, what will happen to soma when, say, a voltage clamp is done at this point of the dendrite. And of course you may map it into a circuit and do, or you may actually run the simulations using neuron, and in neuron you can have more complicated configurations. So we will also quickly see how to start off with a basic circuit like this, right, will behave when we use LT Spice, and then what will be the equivalent thing when we use neuron simulator. First, let us deal with LT Spice circuit simulator. And this is how the window would look when you start the LT Spice. Let us say we want to build a new circuit. We say new schematic. So we have a schematic appearing on the screen with no elements installed now, right? So we can add. So our aim is to simulate an RC circuit first. So we add a. Okay, first we introduce a resistor, and then I want it horizontal, so I have turned it, so that's a resistance R1. Okay, then I want a capacitor, then we can have it in this orientation, so I have it here like that. Then we want to have voltage source, right? So let us say, I think here we have component, then we can say signal, and so we have signal. Okay, so we introduce a signal here. Okay, and we want to move this a little. Okay, so we want to move this, so we are going to place it here, and then we join this to here, and then we want to add a ground. So this is a ground, we have put a ground here. Okay, we want to join these lines, so this point connect to this point. Okay, so they are connected. Now I want to connect this point to this, so that's done. So I think that's basically what we want, right? We want to have the circuit driving the R, driving the C, right? And this is a common ground. Now we want to assign values to this. So let us say, click here, we can assign the value, say 1 kilo, 1K. Okay, and then we want to assign the capacitance, right click here, and then we can put 1 nanofarad. Before maybe moving forward, we'll save this. Save is a draft as draft 2. We don't care right now. You should save it, save as if you want to save it in a particular name. Okay, if you right click there, you choose this pulse. Okay, and you want to specify the various parameters, initially 0, and just to retain the situation we had in our actual simulations, we will put the rise to be 3. So you imagine, so we need something which will, this should be able to give pulses like this, and in our simulation we had 0 and 3 volt here, remember, and this was corresponding to 1 millisecond, so 1 kilohertz. I think that's what we had roughly. Okay, so let us go. So we are trying to set that up. So initially 0 fault time 0, very fast on and off. Then how long should it be on? So if I want 1 kilohertz, then I will put 0.5 millisec as the on time and 0.5 millisecond as off time. That means the period is 1 millisec, right? And I want to run certain number of cycles that we will set on the simulations, and then let us put the run configuration. So I want to visualize, say maybe 5 or 10 cycles, so 5 millisecond is my time for simulation, and that should do, right? We are doing a transient analysis. Okay, now if that is all set up, so we can run. Okay, that seems to work. Okay, now we have the circuit ready. Let us run the circuit. So we have set up the running window by pressing this run. Now you have to choose what all to be showing up. So when you bring the mouse near these lines, it will show either, if it is near a node, it will show such a point as saying that you can put up a voltage probe there. And similarly, you can put up a voltage probe here where it's charging across the capacitor. And if you want to see the currents, when you bring near the line, you will see such a marker, so it will be showing up the currents through that line. Okay, so let us run again. Yeah, so that is the voltage applied is this green. The voltage across the capacitor, as we expected, is this blue, charging, discharging, and of course current through this you can see is this. These things we have dealt with in theory. So this is a simple way of seeing how the circuit will behave without actually having to wire up the elements on the breadboard. Now we may be curious to see, okay, we already tried in the breadboard by putting up a resistor here in parallel with this C, which will turn out to be like the conductance like this between this across the membrane, the cell. So let us do that. So we add a resistor like this here. We use line to connect this. Now we have to assign value for this. So I'll put 1K for this also, similar to what we did in our resistance. So 1K, this is 100 nanofarad, this is 1K, right? And our pulse is so that it is of width 1 millisecond, duty cycle 50%. So now let us run the simulation again. Now our theory and our experiment on the board showed that the time constant, in this case time constant is nearly 1/3 of 0.5 millisecond, should reduce to somewhere here. It should reach somewhere here and reduce nearly half. And not only that, because of this R1 and R2, voltage here will be half of what can be what will be the applied voltage here, right? R2 by R1 plus R2. So now let us run and see whether that is true. So our prediction is that blue line now will reach only to this point, and it will reach earlier than this, meaning somewhere here. So let us run. Yeah, indeed it is true. It reached half the value and it reached faster, right? The max faster. So time constant reduced. So as we said before, when you have conductances, say lead conductance coming in the membrane, the time constant reduces. So this is how you will go about doing the analysis if you have already formulated the circuit schematic like this, right? And as we said, if you don't have an abstract circuit like this, but you have the physical configuration of the neuron or the recording system you are dealing with, then you would go about doing the simulation using neuron. And we saw the basic introduction of how the neuron functions in the theory class. And I also, I think, demonstrated to you this kind of a program in the class. But let us look at it in the particular context of the RC circuit that we are dealing with. Okay. So of course we have to first configure the circuit we are dealing with. So my interest is to have a circuit where there is a soma and there is a dendrite which is very thin and long connected to this, and I'm going to apply a voltage clamp here. Okay, and then I am interested in what will happen to the potential here. Okay, so this is your voltage measuring electrode. Here is the clamping electrode. Suppose you are doing 2 electrodes. Okay, or if you may not have an electrode here, but you want to predict what would happen here, right? Now we have two contexts, two cases. One is there is no leak, other is there is leak. So we will see what happens in both these cases, right? So first we have to define this neuron in the neuron simulator, and then we have to set up a voltage clamp, and then we have to run the simulation while we monitor the voltages as we require. Of course, this is how the view will look in the neuron simulator. This is a soma, and this is a thin neurite. Okay. So let us go about seeing how to do that. Of course, in syntax, we create the two compartments, or we have compartments to segments we have. Of course, we have to have to define the two sections we have, in this case soma and dendrite. And here is a syntax for specifying the physics of the soma. We are using only one segment. We are dividing the volume into only the length into only one segment. So basically 1 voltage point will be calculated. The diameter is a fairly large soma to exaggerate the effects that we are looking at. So 18.8 micron is just hanging out from some previous code I have. Are the resistivity of the media. Okay. Some default value will be there. So currently we start off with a situation where there is no passive thing. So it's commented out. Okay. So later we will do insert these things and see what happens. Of course, we have to specify the parameters of the dendrite. We are dividing it into 10 seconds. So there will be 10 voltage points calculated for this dendrite. They have a uniform diameter of 1.5 microns and length of 700 microns. Now we have to connect the 0 end of the dendrite to the 0 end of soma, and we have connected. We will be connected like this. Of course, this is the setup after I have run the simulation once. So I set it up already and all, run the simulation once. So so this is the 0 end of the dendrite and this is the 0 end of the soma. So they are connected together. Now I want to apply voltage clamp here, right? So we have set up a stimulation object and that has to be in the dendrite, right? And simulate voltage clamp. And now we have to specify the shape of the clamp, right? We want to apply. So we want to stay at -65 for 20 milliseconds, right? And then we want to hold at say 20 millivolt for 20 milliseconds, and then step it down to -65 millivolts. So that's our typical voltage clamp procedure. So that's a basic setup, and we want the simulation to run for 70 milliseconds. Right. So now we have used Neuron to load this program. Okay, and then we have this command prompt in our hands. So let us run the simulation. Okay, I have put fairly low DT so that we can see the time course of the simulation. So init and run. Okay, and I'm monitoring two things. One is dendrite voltage at 1, that is here. That's where the clamp is applied. And of course, I'm also monitoring the voltage in the soma, which is our point of interest. And what you observe is this curve. And as we expected for a circuit where it is just a capacitor, right, no leak, and thin resistance, right, so C, R, voltage source, ground here, okay, externally. So this is a typical RC circuit, right? So that's what we have simulated. This is your voltage clamp. Right. And all these parameters were established based on the physical configuration that you have given in this specifications. Right, now we can ask the question, okay, just like we had for the circuit, if you introduce R here. But here the introduction of R means, say for example, introduction of a passive channel here, correct? So we can go and introduce that in our program. So now soma, inserting passive channel into the soma. Okay. And now what will be the predicted effect here, right? Our prediction should be that now if you did a voltage clamp and somehow suddenly conductances came across this membrane in the soma, then in effect, what all the other voltage gated stuff see on the soma will not be this waveform. We will be seeing a different waveform which we think will be faster. Right, so let us see what happens. Now we have passive inserted inside soma, and we are going to init and run. Did it do as we expected? Okay, so when we run, we see that indeed it does not have any change. So we look at what's the value of soma conductance, passive conductance in soma, and you find that it is 0. So of course, even though we have inserted a conductance in the soma, actually the value of that is 0, so it doesn't make any difference. So of course we can go and give a value. So now we have a finite conductance across the soma membrane, and so that's inserted. Now we init and run, and as expected we can see that the membrane of the soma doesn't reach the clamp voltage first of all, and not only that, it reaches it faster, say compared to, so here is where it reached compared to when it was 0, which reached somewhere here, right? So it reached roughly half the time. So you can see clearly that what theory we would have predicted based on this simple circuit. Now when you insert this, what would happen, and that's very relevant to what happens to the physics of the system when you actually carry out the recording. Of course, there could be other factors like series resistance, which if you didn't compensate, there will be added resistances here and so on. And of course, in reality, there is a capacitance in each of these points, so it forms a cable. But the dendrite is small. That's what you have done. We have sort of assumed that to be negligible, and we can see that that really did not affect our prediction in a large sort of back of the envelope calculation sense. Previously I said that you can view this as a series resistance and a capacitance, a large capacitance at the soma. However, let us look at this onset and offset of the responses, meaning the voltage at the soma across the hypothetical capacitance, right? So if you zoom in here, you can see that after onset of the clamp at this point, the voltage at the soma does not start off immediately. It starts off rising after a delay, and moreover it does not start off in a typical RC circuit abruptly like that, but with a smooth transition. And this is effect caused by this long dendrite, which has R and C elements, which we did not take into consideration when we looked at a simple RC network. So it shows that we indeed need to use a cable theory to explain the behavior of neuron and not simple RC circuit alone. If you look at the offset too, you can see a similar feature. There is a smooth transition and then the exponential fall at the offset of the voltage clamp. So though in bulk it looks almost like the lambda RC element, there are finer features which needs to be explained by taking into account that this is actually a cable.